Okay, thank you so much for that introduction. Let me just share my screen. Okay, you can see my slides?
Yes.
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 Okay. Okay, well, thank you so much to the organizers for the opportunity to speak and for organizing this, going ahead with it in this virtual forum. So, greetings from Canada. I apologize. I haven't had a chance to see much of the conference so far because in my semi nocturnal state in Canada, I'm afraid that the timing of the day almost is perfectly complementary to the time that I'm awake. But I'm trying to shift earlier to catch some of the later talks. Um, uh, anyway, so I'll be talking today about the two-sheeted universe, CPT, analyticity, and the arrow of time. This is about work that began with two papers in 2018 with my collaborators Kieran Finn and Neil Turek on the CPT symmetric universe idea, which was mentioned in the introduction, and then I'll also be talking about a paper which will appear shortly with Neil Turek. Okay, so what's the idea? So here's a this is supposed to be this is supposed to be a brief cartoon sketch of the portion of the universe that we see. So the universe is supposed to be the boundary of this cylinder, and it's drawn as a kind of conformal diagram. But time runs up the page, so we're living on the circle near the top, and then we look back as far as we can towards the Big Bang, and what we don't see all the way to the Big Bang, but we can see back to that circle near the bottom, which is very close to the Big Bang. And what we see there, in short, is ultra simple, as you all probably know. It's spatially flat, homogeneous, isotropic background space-time with a spectrum of scalar perturbations that's Gaussian and adiabatic, and with a scale invariant spectrum of perturbations, and no vector perturbations, no tensor perturbations, no topological defects, nothing else. So it's about as simple as you could imagine, and that's clearly some very important hint about what is going on in the early universe. And the question is, what is it trying to tell us? So the standard interpretation is that so we look back and we know that, let's say, all the way back to 1 second after the Big Bang, the universe was in this ultra simple state. The standard idea is one imagines that packed in before that ultra simple state we see, one imagines that there was kind of a mess that we don't see, and that inflation came along, a period of inflation that we also don't directly see, came along and cleaned up that mess. And I just want to consider here an alternative picture, which is to sort of attempt to take the observations more at face value. Another way to interpret the observations is you look very close to the bang. The closer you look, the simpler things get. A more face value interpretation would be to say, well, maybe it's telling us that as you go towards the bang, things really are ultra simple in the way that we see, and maybe that simplicity extends all the way back to the bang, and try to follow that line of thought and see where it leads. So where does that lead? Well, if that's the case, then the metric near the bang is very simple. It's just it's just a conformal factor, the scale factor squared, times the flat metric. So so if you follow it back far enough, it hits a singularity, but it's a very special type of singularity, the sort of mildest singularity you could hope for, a so-called Weyl singularity, where all that happens is that the conformal factor in front of the metric briefly passes through zero, but otherwise the metric is completely regular and non-singular. And moreover, the conformal factor is just proportional to the conformal time. The scale factor is just proportional to the conformal time near the bang, so it passes through as simply as you could hope with a nice analytic zero. And so a natural thing to do is you can look at the maximal analytic extension of this metric. So you extend the scale factor analytically. You just say tau now runs, instead of from 0 to infinity, you just let it run from minus infinity to infinity. And the first thing you notice about this maximally analytically extended spacetime is that it has a new symmetry that you didn't notice when you were just looking at the top half, which is a symmetry which reflects the bottom and top, turns the hourglass over if you want. So the conformal time goes to minus the conformal time. And the interesting thing about that, as I'll explain more below, is that oops, so let me ask a question, actually. So I see on my screen pictures of everybody, and since I reflect my screen, you see that also. So if it's blocking my slides, it's blocking your view also. Is that right?
No, we see everything properly from our side.
Oh, okay, good.
We see your slide.
Oh, good. So there's a preferred vacuum in this case, a CPT symmetric vacuum that respects this new symmetry of the extended spacetime, and the idea is to imagine that the universe. The hypothesis then is to imagine that the universe takes advantage of this vacuum. CPT is believed to be a very fundamental symmetry of nature, and the idea is that it's not spontaneously broken, but that the universe is actually in the preferred CPT symmetric state. And see what some of the consequences are. So one of the consequences will be that it gives a sort of elegant new explanation for what the dark matter is, and so I just want to go through that briefly. So let me describe to you first in generality how this, a brief sketch of how this CPT symmetric vacuum arises. So here, as an example, let's psi be some Dirac spinner. Okay, so it's a field that to a first order obeys the Dirac equation. So we expand it on a basis of modes. Maybe I'll open the highlighter here. Okay, you can see my laser pointer here. So you expand it in terms of a basis of positive frequency solutions psi and the corresponding charge conjugate negative frequency solutions psi of the Dirac equation. And to quantize, you promote the coefficients A and B dagger in front of those solutions to creation and annihilation operators, satisfying the usual anti-commutation relations, in this case for fermions. Okay, and the problem is, in flat space, there's no problem with this, because flat space has enough symmetry that there is a way to canonically split the solutions of the Dirac equation into which ones have positive frequency and which ones have negative frequency. All inertial observers in Minkowski space agree about that. But in FRW spacetime, which has less symmetry, there is no longer a canonical way in general to split modes into positive and negative frequency. And so, for example, observers at late times and observers at earlier times will in general disagree about that split. And as a consequence, they will, when they take this expansion and use the coefficients A and B to define their vacuum. See, each observer will define the vacuum to be the state that is annihilated by all the A's and B's, according to them. Well, they will disagree about it. So an early observer will define a vacuum, and then a late observer, like us, will define a different vacuum. And according to us, the early observer's vacuum will actually contain a lot of particles. Okay, so in particular, if we look back at our cylindrical spacetime, late-time observers like us, we will take a certain set of modes and call those the positive frequency modes. Those are the ones that are spinning clockwise in the complex plane around our vicinity in time. And we'll use those to define a certain vacuum, which I call 0 plus, the late-time vacuum. But then corresponding observers living at very early times would take a different set of modes that they call the positive frequency modes. They would define an inequivalent vacuum, 0 minus. And these two vacua, neither of them are CPT symmetric. In fact, they get exchanged by CPT symmetry. But the point is that there is another set of modes you can take which do respect CPT symmetry. They have, roughly speaking, they have this extra condition that the mode at time tau is equal to the charge conjugate mode at time minus tau. And so we'd like to consider a vacuum like that. Okay, and so in a bit more detail, here I can take my CPT symmetric mode and decompose it in terms of the late time modes that you and I will define, let's say on Zoom today, on the Earth today. So with coefficients alpha and beta in this expansion, which are the so-called Bogoliubov coefficients, and then a famous calculation shows that if we now ask, if we assume that the universe is really in this CPT symmetric mode, 0 sub 0, and we look at the expectation value of our number operator, so we estimate the number of particles according to us using our late time number operator built from A plus and A plus dagger, that the expected number of particles is given by the square of this beta Bogoliubov coefficient. And it turns out that for the above space-time, you can calculate beta squared exactly, and it's given by this expression exponential of minus a function, which is it's not crucial to get to know the exact function, but just to say it's straightforward to calculate. And so the idea is that it's very much like Hawking radiation. So the idea in Hawking radiation is that the black hole is in one state, but a distant observer defines a vacuum state which is different from that state. And so according to the distant observer, there are particles radiating from the black hole. Well, here the analogous story is that the universe is in one state, a CPT symmetric state, but a late time observer like you or I defines a different vacuum state, and so according to us, there appear to be a bath of particles emerging from the bang. Okay, so how does it apply to dark matter? Well, let's see what the implications are for the particles in the standard model. So let's quickly review what's in the standard model of particle physics. So first we have the bosons. We have the SU3, SU2, and U1 gauge bosons, G, W, and B, and the Higgs field H. And then there's the fermions. So first there are the quark fields. They come in three colors, and there's in one generation there's a down left, up left, down right, and up right. And then again in the first generation there's also the leptons, E left, nu left, the right-handed electron, and the right-handed neutrino. Well, in the minimal standard model there's no right-handed neutrino. But ever since the discovery of neutrino mass in the late 90s, it's been common to imagine that there may be a right-handed neutrino added to the standard model because it gives the simplest renormalizable explanation for the observed neutrino masses and oscillations. But these new right particles are the component of the standard model that haven't been directly observed yet. So, but they have a number of advantages in addition to the one I just mentioned. So let's imagine that they are there. If they're not there, then there simply is no remaining dark matter candidate in the standard model. I mean, if I remove new right from this slide, there's nothing that can be the dark matter. What about if I include new right? Well, I remember that there's the other thing I haven't mentioned so far is that the fermions come in three copies here. There's three generations of fermions, and it turns out that so there's really three right-handed neutrinos now. It turns out that we know that two of them cannot be the dark matter because they necessarily decay. They're not stable. But the third one could be, it's compatible with everything we know that the third one is stable. And if it is the only dark matter particle candidate in the standard model. It's the last remaining, it's our last hope with the standard model. So let's try to imagine for a moment that is the dark matter, that right-handed neutrino is stable, which amounts to asserting that the standard model has a certain symmetry under nu right goes to minus nu right. Well, then, using the formula on the previous slide, where I was describing the Hawking radiation process, we can ask, what is the what is the number density of such particles that a late time observer like us sees radiated from the bang, and you can calculate the ratio of the number density of those dark matter particles to the radiation density, and it's given by some dimensionless coefficient c, which can be calculated in terms of 2's and pi's, and times the ratio of the dark matter mass to the Planck mass to the 3/2. And so using this, you can ask, well, what mass do we have to have in order to match the dark matter density? And it turns out to be, you can get a precise prediction. It has to be 4.8 times 10 to the 8 giga-electron volts. So if one of the neutrinos has that mass, then that turns out to be a very nice candidate for the dark matter, using just the standard model particles. Okay, if that's true, then it makes an important prediction about the neutrino sector, which is that one of the 3 light neutrinos, the neutrinos that we have directly observed, one of them should be exactly massless. Okay, and so that will be tested by laboratory and astronomical observations in the coming up in 2 different ways. So first of all, it means that the predicted sum of the 3 light neutrino masses, which of course many cosmology experiments are currently trying to measure, we predict that if our dark matter model is right, then that sum should be the minimum possible value, which means that it should be 0.06 eV electron volts if the neutrinos have the so-called normal hierarchy, or twice that value if they have the inverted hierarchy. Okay, and so here is a slide showing how forthcoming experiments should be able to test that and rather rule that prediction in or out. Also, it ends up making a very specific prediction for the rate of neutrinoless double beta decay. So in this model, all of the neutrinos, the light neutrinos and the heavy neutrinos, have to be Majorana neutrinos. And so the light ones, and so they cause a process called neutrinoless double beta decay, which is again being searched for in laboratory experiments. And if you know that one of the light neutrinos is exactly massless, it turns out you know very accurately, you can predict what the neutrinoless double beta decay rate is, and it depends again on whether the neutrinos are in the inverted hierarchy or the normal hierarchy, but it corresponds to the prediction corresponds to the left edge of this plot. And in any case, the basic idea is that the next generation experiments will be able to rule out the inverted hierarchy prediction, or rule it in if it's right, and then the subsequent generation of experiments, should we choose to build them, would hopefully be able to get down and rule out the normal hierarchy prediction as well. Okay, very good. So far, I've been thinking about the past, looking back toward the bang. Now let's also think about the future. So, it appears that when we look back toward the bang, as I was mentioning, we see a radiation-dominated epoch very close to the bang. On the other hand, it appears when we look to the future that we have a dark energy-dominated or vacuum energy-dominated future ahead of us. So those are the 2 sort of asymptotic regimes, it seems, or that's the sort of simplest possibility consistent with observations. So let's start by considering the simplest cosmology with those properties, that it's asymptotically radiation dominated near the bang and asymptotically vacuum dominated in the future. So the simplest cosmology of that sort is just has radiation and vacuum energy, and so this is the Friedmann equation for such a universe, where the r over a to the 4th is the radiation energy term, and the lambda is the vacuum energy term, and then we have kappa over a squared, the curvature term. So this is just the Friedmann equation written in conformal time. So I'm considering this simplified universe to start with the ordinary matter taken out, or the non-relativistic matter. I'll put it back in a moment. But because in this simplified universe you can solve for the scale factor exactly, and it's given exactly in terms of the so-called Jacobi elliptic function Sn. a very beautiful analytic function. It says here alpha, beta, and m are three constants that are determined in terms of these other constants, r, lambda, and kappa, in a way that's not crucial. But so we get this nice analytic solution, and if we look at it, well, the focus on the solid blue curve. That's how the solution looks when for the physically relevant case, if the universe isn't too curved. This is showing that the universe. So here I'm plotting the scale factor on the vertical axis versus the conformal time eta along the horizontal axis, and so the universe starts at a bang here at a simple 0, and then it expands to the de Sitter boundary, which in this language just corresponds to a simple pole of this function. But you notice that if you analytically extend the function, because it can be analytically extended, it just has a simple 0 here and a simple pole here, so there's no ambiguity about extending it. It has, first of all, you notice that it's periodic with twice the conformal time. So if the distance from the bang to the pole to the de Sitter boundary is called eta star, then the period of this function is 2 eta stars, and it ends up having two parts to it. It ends up having a sort of branch of positive scale factor and a branch of negative scale factor, and then that behavior repeats. And it also has a reflection symmetry around the bang, and it has a reflection symmetry around de Sitter infinity. So that, taken all together, if you look at the analytically extended spacetime here, you can think of it as the following picture. It's like the extended two-sided cylinder I drew earlier in the talk, but I'm going to take the part below the bang and I'm going to pull it up inside the part after the bang to form a sort of two-sheeted cylinder. So in other words, here I start at the bang. As eta, the conformal time increases, I eventually reach the scale factor eventually reaches infinity in the far future. But then as I continue, it goes to negative infinity, and as I continue back down the inside of the cylinder, it contracts back to 0, and then back around to another. Anyway, it's periodic. Okay, so we have this two-sheeted cylinder picture, and the reflection symmetry just corresponds to saying that if I take every point on the outside cylinder and swap it with the neighboring point on the inside cylinder, that is an isometry of the space-time under which the metric doesn't change, but the tetrads, if you want, the square root of the metric, which the fermions couple to, flips sign. So let's have a look at the analytic structure of this solution in the complex plane now. So here I've tried to show the structure in the complex plane, and you see it has this beautiful. It actually, in addition to the periodicity we've been looking at so far, we've been looking at a plot of this solution along the real eta axis, the real conformal time axis here. But now I'm showing it in the complex conformal time plane, and you see it has this property that all elliptic functions do, which is that they're the special functions that are doubly analytic in the complex plane. So they have two different directions in which they're doubly periodic, I should say. They have two different directions in which they're periodic. So you see it has a periodicity in this direction as well. So an interesting thing to note, sort of evidence that we should take this analytic structure seriously, is that, well, as you know, we can take the conformal time eta and we can convert to physical time t by taking the integral of a d eta. But now if we want to take the integral of a d eta from eta equals 0 to eta equals eta, well, that integral is going to depend now on how we go around the poles of this function. So in this function, the middle of every blue circle is a 0, but the middle of every white circle is a pole, and the poles with positive residue are marked with a plus here, and the poles with the opposite negative residue are marked with a minus. But so since the integral is going to depend on exactly how it winds around the contour, and how the contour winds around the different poles in the complex plane. That's an arbitrary choice. And as a consequence, the definition of t is going to be arbitrary up to a constant shift by any integer multiple of delta t, which turns out to be 2 pi I over the Hubble constant in the asymptotic de Sitter space. That's just a consequence of looking at what the residue is contributed by each of the poles here. But if you have a time coordinate that is ambiguous up to constant shifts in the imaginary direction, it's famously the fact that corresponds in field theory to a system that's at a finite temperature. And so you can work out what is the temperature implied here. And well, in this way, you exactly recover a famous formula, which is the temperature of de Sitter space, that it's the Hubble constant of de Sitter space divided by 2 pi. Okay, very good. So I'm getting close to the end here because I wanted to leave time for questions. So I'll just be brief. So now so far I've talked to you about the analytic structure of a universe that is simpler than our universe and is just has radiation and cosmological constant, which is designed to have just the asymptotic regions near the bang and near the future that we want. So now let's re-add some matter. So the simplest example it would be to add a massive scalar field living on this background. The interesting thing, which I want to point out, is that in keeping with what I've said so far, I would like to look for solutions that for this scalar field that respect both the symmetries and the analytic structure of the background that it's living on. So I want to take this double-sheeted picture seriously, as we did before, and see what it implies about the matter. The interesting thing to say is that the first thing you notice is that, well, the solutions to the above Klein-Gordon equation, and this is also true for the Dirac equation, I'm just using the scalar case as the simplest example. The solutions are completely analytic at the bang, or meromorphic. They can have a pole. Whereas they're not analytic, so they're analytic down here, but they're not analytic up here at future infinity, at the de Sitter boundary. They have an essential singularity there. And so that means that when I combine the requirement that they have this symmetry under reflection between the two sheets, if I combine that with the analyticity property down here, that turns out to imply a boundary condition on the solutions. That's equivalent to saying that the solutions satisfy a boundary condition, which is either Neumann or Dirichlet, anyway. It implies a boundary condition, which let me not go into the exact details, but down here at the bang, because the point is that that I can get across the bang in 2 ways. One is I can get across by using the reflection symmetry, but the other thing is I can get across by analytically extending around the bang. And the requirement that those 2 methods of crossing from one sheet to the other agree with each other imply a boundary condition down here. But because up here, there's only one way to get across. I can use my reflection symmetry, but there's no way to analytically extend across the bang. There's no corresponding boundary condition up here. So that's very neat, because that's exactly what one wants from the standpoint of the thermodynamic arrow of time. So, a fact that we observe in our universe is that the entropy appears to have been much lower at the bang and then has been increasing ever since, and so far as we know will increase until future infinity. And the question is why? Why does the arrow of time point that way? Why does the direction of entropy increase point away from the Big Bang? So this gives a very elementary possible explanation for that demanding that the matter fields in the universe respect the symmetry and analyticity properties of the underlying spacetime implies that they satisfy a very restrictive boundary condition at the lower boundary, but no boundary condition at the upper boundary. So it's exactly the conditions you would need to explain the arrow of time. Okay, so I'm getting close to the end, so I'm just going to briefly say a few other things that I didn't have time to talk about in detail. So this picture makes a number of other predictions or explains a number of other things, and then there are a number of things which are still open, which we would like to explain but do not yet claim to do. So first of all, it predicts that there are no primordial tensor perturbations. So that's another way to test the theory. The same theory that predicts that the neutrinos, the dark matter particle is produced coming out of the Big Bang, predicts that the gravitational waves are not. It explains why there are no primordial vector perturbations. For the scalar perturbations, an observed fact about the primordial scalar perturbations is that we only see the growing mode perturbations. There's no decaying mode perturbations. So there's two solutions for the primordial scalar perturbations. We see that the universe is purely in one of those solutions without the other one. The normal inflationary explanation for this is that the mode has been stretched far outside the horizon, and that has damped away the other solution. But here we have a different solution, which is that the symmetry around the bang cuts out one solution and leaves the other one. And so, but it cuts out it leaves exactly the solution that you want, the one that, and so this is why this primordial scalar perturbations are synced up in phase. It's why you eventually, at the time of the CMB, see that the scalar perturbations were oscillating in phase with each other, and so you see this ringing pattern in the CMB. Whoops, sorry, I pulled out my headphones. So we do explain that. We give an alternative explanation for that. Now, what do we not yet claim to explain? Well, first of all, we would like to give first of all, is homogeneity and isotropy. You see all the discussion so far. I've been assuming a background which is Friedman, Robertson, Walker, and once I assume that, the analysis gives self-consistent results about that assumption, but ultimately we would like to explain where homogeneity and isotropy is coming from. A very important thing is that although we get the phase of the primordial scalar power spectrum, we already claim to explain that. The actual power spectrum we don't yet claim to explain, although we're working on a paper about that, so I hope we will. Also, we think this gives a new perspective on how to define the boundary conditions for quantum cosmology, using that the fields in the path integral should be that the paths that one includes in the path integral should lie in this double-sheeted picture and have the appropriate symmetry. And so, in the interest of time, I'll just leave that.